How expansion occurs. Expansion occurs on heating as the heat energy increases the moment of the constituent molecules. The molecules collide with and repel each other. This increases the intermolecular spaces. The entire structure is enlarged. The substance occupies more area than earlier, and we say this as expansion of the substance. Liquid and solid expansion differs, as the molecular structures of the liquids and solids are different. They show difference in expansion. Liquids expand more than solid for the same change in temperature. The bonding of molecules in solid is more rigid compared to that in liquids, because of which liquid molecules move freely and rapidly, thereby achieving faster expansion than solids. The intermolecular distances after molecular collisions are more as compared to those in solids, and thus liquids show more expansion than solids for the same change in temperature. Let us see an experiment that shows that expansion of a liquid increases its volume. Take a flask, fill water up to its brim and close it with a rubber stopper. Insert a narrow tube in the flask through the hole of the stopper. Now heat the flask and see what happens. Surprisingly, the water level first drops down and then starts rising. Let's see why this happens. On heating, the heat energy first reaches the solid flask and expands the flask. This increases the width of the flask, and this makes water level to drop down. But soon the heat energy rises the water temperature also, and water starts expanding. The water level rises and we can see the increase in volume of water. Thus, we have learnt expansion in liquid changes the volume of that liquid.
Boyle's law says that for a given amount of gas at fixed temperature, pressure and volume are inversely proportional. P is proportional to 1 over V. You can write this mathematically as P equals K over V, where P equals pressure, V equals volume, and K is a proportionality constant. We can rearrange this equation so it reads PV equals K, or the product of pressure and volume is a constant, K. Charles's law says that for a given amount of gas at fixed pressure, volume and temperature are directly proportional. V is proportional to T. You can write this mathematically as V equals KT, where V equals volume, T equals temperature in Kelvin, and K is a proportionality constant. We can rearrange this equation so it reads V over T equals K, or the ratio of volume to temperature is a constant, K.
Avogadro's law. Amedeo Avogadro, an Italian scientist, proposed that under the same conditions of temperature and pressure, equal volumes of all gases contain the same number of molecules. Here is an illustration. The law can be explained by correlating the number of molecules present in known volumes of gases. Here we see a volume V of some known gas which contains n moles of the gas. We observe that a volume of 2V, or twice the former volume, contains 2n moles of the gas. This can be mathematically stated as V is proportional to n, or V is equal to Kn, where K is constant. Now click on the next button. Alternatively, the law can be comprehended as we see here that if two different gases are considered of equal volumes and under same temperature and pressure, they will contain equal number of molecules.
Good morning, students. We are going to see about ideal gas equation. Ideal gas equation is an equation which relates all the properties of an ideal gas. Ideal gas obeys Boyle's law, Charles' law and Avogadro's law. According to Boyle's law, we get the formula PV is equal to constant, equation 1. According to Charles' law, V by T is equal to constant, second equation. According to Avogadro's law, V by N is equal to constant, third equation. We are going to combine first equation, second equation, third equation. All the numerators we are going to combine top, all the denominators at the bottom. So we get PV by NT is equal to constant. We get the fourth equation. The above relation is called this fourth equation is known as the combined law of gases. If you consider a gas which contain mu moles of the gas, the number of mu times the Avogadro's number is Na. So, what we are going to do in fourth equation, this value of N, we are going to substitute as mu times of Na. So, this N you are going to substitute in the equation 4. So, first we are going to substitute 5 in equation 4. First we are going to write PV by NT is equal to constant, equation 4. Then, we are going to substitute in the fourth equation. PV by, instead of N, you are going to substitute mu NAT, that is equal to constant. That is sixth equation. The value of the constant in the above equation is taken to be Kb, which is called Boltzmann's constant. What is the value of Boltzmann's constant? 1.38 10 to the power of minus 23 joule k to the power of minus 1. Hence, we have the following equation. PV by mu NAT is equal to Kb. Instead of constant only, you are going to apply here Kb. So, we get the seventh equation. Next step, this mu NAT, you are going to bring to the right hand side. When it comes to the right hand side, it will come in the multiplication side. So, we get mu Na. T is already here. So, this underline this Kb mu Na. This alone you are going to take as R. And it is known as universal gas constant, whose value is 8.31 joule mole to the power of minus 1 k to the power of minus 1. Since Kb mu Na is taken as R, we are going to substitute this as R here in this place. So PV is equal to RT. We got the ninth equation. Therefore, ideal gas equation is also called as equation of the state because it gives the relation between the state variables and it is used to describe the state of any gas. Thank you.